So we'll start the session at 6:10. If someone joins, it's fine, or we'll start. Okay, so we'll start the session now. I'll just share the screen here. Right. Hello everyone. So today we are going to discuss about or we'll talk about the tutorials for the week 7 lectures. I hope you guys have gone through the lectures because so now we are shifting from the hydrological components of watershed to the watershed management part, or uh, like what are the types of watershed and so on, right? So uh, before that, let me introduce myself. So, I'm Balram Shah. I'm the PMR for TA for this course, that is Watershed Hydrology, given by Dr. Rajendra Singh from IIT Kharagpur in the Department of Agriculture and Food Engineering. I'm a PhD scholar at Interdisciplinary Center for Water Research at Institute of Science, Bangalore. Okay, so with this, let's start. Before that, I will share the screen for this. Okay. And I'll switch on the video so that helps in the bandwidth. Yeah, so share it from here. Right. I hope you guys can see the screen. Yes, with that. So, okay, so before moving on, we'll start it with the first little button. Okay, so in this week, what we have started with, again with the watershed. Just to reiterate that what is watershed or what is the catchment? Can anyone just tell me what is watershed or what is catchment or what is basin, river basin, whatever we call? So we know that watershed is the area, sorry, uh, so area of the Earth's surface within the physical boundary, which is defined by topographic slopes that divert all the runoff to the same drainage mode. So this means what? That an area in which whatever input water we have, say precipitation and all, if it flows through a single outlet, if it converges to a single outlet, we call that area as watershed, right? So we have studied all this. Now we can consider this watershed as a system also. So there are system concepts in which what we do generally, what we take one input and there is some system from where we get the output. So let's say output is QT or Q tau. And this, let's say the system omega. Okay. So this is the system concept. We can use this. We can consider the watershed as a system, and then we can proceed because it will help us to work in an efficient way. That's why we go to the system concept sometimes, right? So this watershed can be classified into various different types of watershed, right? And it can be based on different things. It can be based on the shape, based on the maybe land use, land cover. It can be based on maybe the size, length, right? And so on, right? So the watershed can be classified into several types of watershed based on which factors we are thinking. Like if let's say we are saying that by size, then watershed can be classified into small, medium, and large catchment. Right? It can be considered as very large catchment, but we consider. So let's say if the area of the watershed is less than 250 kilometers square, we call that as small watershed. If the area is between 250 to 2500 kilometers square, we call that as medium watershed. And if it is more than that of the 2500 kilometers square, we call that catchment as large catchment or large watershed. Right? But these again, this classification varies based on if you go through the papers, if you go through the articles, research articles and all, you'll see that sometimes several researchers consider different size or say different area, and based on that they classify the watershed. Right? So let's say if you have a small watershed, what do you think? What is the main difference, or why we are classifying this large watershed or small watershed? Anyone? Okay, so we are classifying this watershed because let's say a large watershed, if you consider, in that case, what will happen? The channel network or the channel phase, it will be very clear, it will be very well developed and well defined, right? And in that case, the channel storage will be dominant. So we have seen that in the watershed, when rainfall occurs, the main part is channel flow or the overland flow, and then it flows into the channel stream. So if you just see the sorry. Hello, can Mr. Chetan, do you have anything to say? Okay, so when we talk about the large catchment, in that case, the channel network or the channel phase, whatever is there, it is well developed and well defined. So in that case, what happens that the if we consider the watershed as a linear or the system of the watershed as linear, it will be uh, a good assumption, because in the large catchment the system or the complexity becomes very stable, and that is why we can work on the large catchment easily. Okay, so if let's say if a high intensity rainfall occurs, right, but it happens for a very short duration, then what will happen? Whether small catchment will be more affected or whether large catchment. So what I'm saying, so let's say uh, a high intensity rainfall is there, high intensity rainfall, but for a short duration. Okay, so whether this will affect small catchment more or the large catchment more? Because see, if it is small catchment, the whole, if not only in terms of size, but if you go in terms of space, or you go in terms of time, in both the cases, what will happen in the small catchments, or if it is, if you work with smaller time scale, in that case the watershed having smaller area, or the watershed with minimum lesser time scale will be more complex. So as you go more smaller and smaller, then what happens, the hydrology and the work becomes more complex. And here, if, let's say if you consider a small catchment, and if a high amount of rainfall is happening, high intensity rainfall, and it is happening for a short duration, then what can happen? Flood like situation can arise, right? So in that case, smaller catchment is much more affected than that of large catchment, right? So in large catchment, the channel network will be much more prominent, but in smaller catchment, the channel network will be not that prominent, because in that case, it is possible that it is smaller catchment and in which only in which only drains or overland flow is happening, right? So these are the watershed definition by size. Then watershed can also be classified, as I say, by land use, on the basis of land use. So land use, as in there can be different. Let's say in one catchment or one area can be a forest, area can be agricultural, when one area can be urban, maybe mountainous. So like that, based on that, the watershed can also be classified into agricultural watershed, then urban watershed, forest catchment, the mountainous catchment, desert catchment, coastal watershed, wetlands can also be there, and mixed type can also be there. So mostly which we work on, let's say in India, if you see, if you go for a large catchment, in that case, what will you see? That there are different geographic land use that are present in that catchment. For example, if you consider Ganga Basin, in that case, what is happening? It starts from Gangotri Glacier, so it has mountainous part in it, right? So it has glaciers, and then if you move more downwards or more downstream, you can see there are agricultural land. There are then urban area is there. Okay, in between forest also comes. At the end, if you come, then you will see wetlands are also there. So that will be a mixed kind of watershed. Okay, and again, this agricultural watershed, urban watershed, forest watershed, all this itself is a vast subject. So let's say if you consider urban hydrology itself is a big subject, which let's say is a 3 grade course for some 1 semester course kind of thing. Okay, so like that, all this has its own importance, right? So in urban hydrology or in urban watersheds, what is there? Most of the land use are covered with buildings, roads, streets, pavement, etc. Right? So what will happen? The most of the soil is covered with surface, or maybe most of the surface is impervious now. In that case, let's say if the precipitation is happening, whether it will be infiltrating more or less, it will be less, because the soil surface is now covered with impervious surface. So infiltration will be less, but what will happen? The runoff will increase, right? And as in the urban watershed, the all the structures are artificially built. The natural pattern, let's say, small stream is there, right? Now if you do something there, if you do human intervention there, in that case what will happen? The natural pattern, whatever is there for the water flow, will not be uh, will not be natural, because it will be altered, right? So like that, we have several other, all these can be studied. So all these things has been explained very nicely in the lectures. I suggest you, if you have not gone through the lectures, go through the lectures once, because in that it will be easily clear, right? Okay. Okay. So these are the by size, by land use. Then it can also be, as I mentioned, that it can be by shape, shape also, right? So if you see by shape, then watersheds can be classified into elongated watershed. So before that also, before this lecture also, we have seen several watershed based on the site. Sorry, shape. Can you tell me any watershed which you have seen, different watershed which we have studied before this lecture based on the shape? See, one I wrote only, right? So it can be fan-shaped watershed. It can be broad leaf-like structures, or it can be elongated. So, so let's say if it is elongated, it will be like this, and all the streams will be something like this, something like this. Something like this, isn't it? Okay. So you can see this is an elongated, something like this. It is, right? So like this, there can be different shapes based on which we can classify the watershed, right? So now with this, we'll move to the some of the assignment questions first, then again we'll come back here. Okay, so the first question that we have is, small watersheds are highly sensitive to, just now we have discussed this, can you tell me any guesses? So we have small watersheds, right? And here we are talking about the rainfall, right? So let's say if we have a low intensity rainfall, then what will happen? The small watershed, if low intensity rainfall is there, it can accumulate very slowly, and then the response will be seen. So the small watershed will be highly sensitive to the high intensity rainfall, but which occurred for a small duration or short duration, right? Because that will affect more, and it can create a flood like situation. So the correct answer will be C, that is high intensity short duration rainfall, right? Okay, the next question is, a fan shaped watershed will result in a dash peak of runoff than fern leaf shaped watershed, right? So just now we have discussed like what is the fan shaped, something like a, it kind of elongated one, right? It will be something like this, something like a big hand fan kind of, right? Something like this. So this is kind of fan shaped catchment or fan shaped watershed. Okay, and along fern shaped mean it was the elongated one that we have seen is the fern shaped catchment. Right. So here what is mentioned that a fern shaped catchment will result in dash peak of runoff than fern leaf shaped watershed. So in the fern leaf shaped, what we know that the water will flow very fast, right, as the runoff, because it is an elongated one. So the water which starts from, let's say, the remotest place of the watershed, and what will happen as because of its shape, it will very like quickly it will come to the outlet point. Whereas if you see the fan shaped one, if you consider the remotest place, let's say this point, from this it will take a lot amount of time, which you have seen in the fern shaped catchment. So in that case, what will have happen? The peak of the runoff in the fan shaped catchment or the fan shaped watershed will be higher than that of the leaf shaped watershed, right? Fern leaf shape. So the correct answer will be A. Okay. Uh, okay. So this we have seen in the forested catchment in the lectures. So if all the vegetation in a forested catchments are removed, the water yield is expected to increase by. So firstly, mm, so what do I mean by forested catchment? Forested catchment means the catchment which is fully covered with forest, right? Fully covered with vegetation kind of thing. Now, let's say if all the trees, or we cut down all the trees of that catchment, then what will happen? Anyone? Okay. So let's say if you remove all the trees, in that case, what will happen? The water holding capacity of the trees will not be there. So the soil retention will be, water retention of the soil will be very less, right? And hence the water yield will increase. So the here in the question it is water yield is expected to increase, that we know, but the question is how, by how much? Okay, so in the lectures we have seen, it is mostly if you cut down all the trees from the forested catchments, the water it will increase by 20 to 40%. So the correct answer will be 20 to 40%. Okay. Okay. So the next question is, for more compact watershed, the time base will be, yeah, okay. So time base we have studied previously. So remember the hydrograph that we have studied. So let's say this is the this is the input. Input as an effective rainfall, right? Or excess rainfall. And this is the output, right? This is the time, and this is the discharge. Let's see. Correct? So in the hydrograph, you remember the time at which the this curve starts, from there to the end of the hydrograph, we call that as time base. It is TB, let's say. So here TB is the time base. Correct? So now, what is the question? Question is for more compact watershed. So in the let's say a watershed is a very compact watershed. In that case, what will happen? The time base will be, sorry, will be very short, right? Why? Because it is a very compact kind of watershed. In that case, what will happen? The rainfall, let's say any rainfall happened, 1 centimeter of rainfall happened. In that case, what will happen? Whatever water was there, it will very quickly move to the outlet, right? Or till that time the rainfall ends. So in that case, what will happen? The time base will be very short. So the correct answer will be B. That is short. Okay. Okay. Next question is, which of the following is a characteristics of a reticulate drainage pattern? Okay. So before this, we'll explain in detail. Okay. So like see, this is the elongated watershed, right? Like that we have seen the fan shaped watershed also. So in this, what you can see, there is a this the whole red colored thing inside. You can see it's called the drainage network or channel network. Drainage network, correct? So now this drainage network can follow few of the we have like observed that it can follow few of the patterns. So let's say if the tributary is so here, let's say if if the main stream is something like this, and the tributaries are joining something like at some acute angles, something like this, right? So most of the tributaries you can see are joining at tributaries joining at acute angles, right? So this pattern we call as dendritic pattern. Dendritic pattern. Okay. So like that, there can be parallel drainage pattern. Okay. So in parallel, what we see in parallel drainage pattern, we see that it is kind of all the streams that is there are mostly parallel like, and it so parallel will create what kind of catchment? It will create elongated kind of catchment, right? And most of the tributaries will be long, and it will be straight. And tributaries will join at acute angles, but it will be very small acute angles because it will have to be an elongated catchment. Then we have trellis catchment. So in trellis kind of pattern, what you see that the very small or very small size or short straight tributaries are there, in which tributaries join at almost right angle, right? Then comes the rectangular kind of pattern. Okay, that also I'll get something like this, maybe something like this. So here what you see, most of the network or most of the things that you can see are following, all the tributaries are joining at right angles. So tributaries bend and join almost at right angles. So can you give example in what kind of catchment this kind of tributaries or this kind of drainage pattern is visible? Anyone? No? So this kind of pattern is mostly visible in urban watersheds, because see in urban watershed it's mostly human made, right? It's mostly human made, and the human are very what they do is they more make very perfect kind of channels and all, and because of that most of the tributaries that you will see join at right angles or something like that. But it's not very compulsory that it is in watershed. It can be there in the different other types of watershed also. Okay, then comes the reticulate. So drainage network can be dendritic, can be parallel, can be trellis type, can be rectangular, can be reticulate. So in reticulate, what happens? Most of the tributaries will cross together, forming a cycle. So most of the tributaries that you will see are joining at some place, and again it will come back to that point only. So kind of a cycle is there, right? So in the reticular type of drainage pattern, what we observe is most of the tributaries cross together forming a cycle. Okay, so all these watershed will have different characteristics, and also we'll see that later. But before that, we'll see that question once, right? So the question is, which of the following is a characteristics of a reticular drainage pattern? So the first option is tributaries join almost at right angles. So at right angles, we know mostly which joins are the rectangular pattern, drainage pattern it follows. So this is not the option. Next, tributaries form a tree-like structure and join at acute angles. So we know that tributaries which form a tree-like structure and which join at acute angles are mostly dendritic pattern, right? Third is the tributaries are parallel and long with minimum branching. So in that case, that will be parallel drainage network. Okay. Next option is tributaries converge towards a central point, forming a radial pattern. So here it is mentioned radial pattern. Radial pattern means it will be like let's say a one point is there and all the water is coming in that point again, right? So here it is forming a cycle, right? So tributaries are converging towards a central point, which forms because of which it is forming a radial pattern kind of thing, right? So let's say, for example, we'll see. So let's say if this is a central point and the water something like this. I'm just making something, okay, something like this. So you can see it is having a radial pattern, or we can say this has a sorry this has reticulate pattern, correct? So the correct answer will be D. That is, uh, tributaries which converge towards the central point forming a radial pattern follows the reticulate drainage pattern. Okay. Next we have this. Okay. So the watersheds, we have seen that it can have different quantitative characteristics. It can have physical characteristics such as watershed area, then what is the shape of the basin, what is the slope of the basin, what is the size of the basin, and where is the center of gravity or center of the mass of the basin. Then these are the physical characteristics of the basin. Then there can be channel characteristics also. Channel characteristics like such as channel order, channel length, channel slope, channel profile, drainage density, all and all. So we'll see all those very fast. So whatever we'll deal with is the geomorphology of the watershed, right? So what is the geomorphology of the watershed? So it's like geomorphology, right? So the study of the morphometric characteristic or the characteristics of the we call that as watershed. So in this we'll study the characteristics of the land surface and the channel characteristics of a watershed, and that is why we call this as geomorphology of the watershed, right? So as I mentioned that the important role after let's say a rainfall event, what we see, we have overland flow, and along with that there are channel flow, right? So, so we'll start with that. So this morphological, if you were just right, morphological characteristics. So what we'll see, what all characteristics? Firstly, the 1D in the one dimension, we'll see the linear aspects of the watershed. With linear aspects means, so let's say a river, so that follows in let's say one dimension, right? So linear the what is the length of that channel, then what is the order of that channel, what is the width of the channel, what is the perimeter of the channel. So all this will come in the uh, linear aspect. Then comes the second dimension, that is areal aspect, or the aspect which deals with the area. and then comes the third dimension, or we call that as relief aspects. Relief aspect as in which deals with the elevation. So in this, relief aspects are related to the elevation difference between the reference point in the watershed, right? So linear aspect, as I mentioned, can be based in length, can be based in width, perimeter, stream order, stream number, then bifurcation ratio, stream length, length of ratio. So okay, so we'll start with the linear aspect. I'll just touch upon these linear aspects. So firstly is the basin length. So this, what is basin length? So let's say if you have a watershed, something like this. Okay. So basin length can be, so let's say if you start from any point, okay, let's say from here to here, let's say this is the longest line or longest straight line that we can create in this watershed, or in, with this shape, then that we'll consider as the basin length. So this is one of the definition. Second definition can be the greatest distance between the outlet point. So let's say this is the outlet point, and from here this is the greatest length. So here greatest length from outlet, to any point in the perimeter of the basin. Or let's say if there is some river, let's say the river. So let's say this is the channel. Okay. So the length of this channel, we call that as basin length. Okay. So this is the length of the mainstream. So based on how you define the basin length, you can consider that basin length. Okay, so this basin length can be defined in all three of these ways. So most common is the whole length of the mainstream. We consider that as basin length. Okay, so basin width is like perpendicular to the basin length that we have considered will be the basin width. Then basin perimeter is like, basin perimeter is the outer boundary of the watershed that encloses the area. So the total perimeter that you can see is the basin perimeter. Okay. So basin. Then we have stream order. Okay, we'll see the stream order in the next page. Name is stream order. So let's say if you have a drainage pattern, something like this, or drainage network, something like this. Something like this. Okay. Now you can see there are several smaller streams which are joining, and then it is coming to the mainstream of the larger stream. So let's say for here, if you see, I think that for your example. So there, let's see the first line, this line and this line is the smallest stream that we can see. So what we give, we start from 1. So this one is having a stream order of 1. Now both these streams with order 1 is joining. So this stream, this stream that you can see is order of 2. And again, let's say this is a big stream which is done by 2 big streams, and the order of this is 2. Now if both of these streams joins, then again this stream will be 3. Okay, and let's say again the left side one is having a stream order of 2. Now if both these streams again joins and a new stream is forming, right? So the highest stream order it will have, because it will have the um, contribution of both the streams. Now again you see 3, and let's say if this is also 3, then this will one become 3. Sorry, this one will become yes, this one will become 4. And then again 2 4s are there, it will become 5. Let's say if this is also 4, and again it will stay 5. Then again let's say if this is the 5 order, then this becomes 6, and then it might be possible that this stream is having the fastest stream. So the stream which is at last coming to the outlet will have the highest stream order, correct? So the one which I mentioned is the stream order as defined by Horton Staller. Horton and Staller both are different. So Horton is one way, Staller is another research. So Horton Staller stream order. So in QGIS also, if you see it, we will see Staller order, right? Okay. So this is the concept by Horton and Staller. Whereas there are several other concepts given for the stream order. One of them is the Shreve stream order. Okay, I'll write it here. This is the Horton Strahler. Okay. Now let's say again we have something like this. Again, let's say this is the channel stream. Now you see, let's say if two streams are having stream order of 1 and 1. Now according to this Shreve's, what you can say that whatever whenever two streams of 1 are joining, it will become 2. So same stream order, if it is joining, it will be the summation of both the stream order. Okay, so now if let's say if this is the second order and this is the first order, in hotels what was happening, it will be the maximum stream order whichever we had. So now if this 2 and 1 joins, in case of Shreve, it will become 3, the summation of both the stream order, and so on. So let's say if this is 1, this is 1, this will become 2. Now see, 3 is joining and 3 is joining and 2 is joining, then here it will become 5. Okay, so let's say if this is the 1, this will become 6, something like that. Okay, so this is the Shreve stream order. Okay, any questions on stream order concept? Okay, so we'll move to the questions now. I hope till this it is clear. So I was mentioning that there can be uh, different other linear aspects also, like stream number. So total number of, let's say if you have several streams of stream order 1, the total, if you do the total length of that, the total number of the streams which is having the order of 1 will be the stream number for that one. So let's say in this case, in the figure 1, let's say this is figure 2. In figure 2, what will be the stream number, that is NU for 1 or stream order 1. See how many 1 we have: 1, 2, 3, 4, 5, 6. Let's say this is also 1. Yeah, so 7 is the stream number for order 1. Similarly, if you see NU for the second order, then it will become 1, 2. So 2. NU for third order, it is 1. Okay, something like that. So this is the stream number. So then we have bifurcation ratio. What is bifurcation ratio? Bifurcation ratio is defined as the ratio of the stream numbers per like stream order of first. So let's say if it is first order, then U plus 1. Okay. So this means, so bifurcation ratio can be like NU1 by NU2. That will become 7 by 2, that is 3.5. So these are necessary. Why? To understand like what is the characteristics of the catchment and so on. Okay. Other than that, there can be stream length, when where we add up all the length of the stream of some order and then we get the mean stream length. Okay. Then we have stream length ratio and length of overland flow and so on. Okay. So this one was the 1D aspect. Second was the 2D aspect, that is the areal aspect. So in areal aspect, what we have the basin area first of all, right? First of all, we have watershed area. So watershed area is simply the whole area that you can see of the watershed is the watershed area. Okay. So it can have two components. It can have stream area plus the interbasin area, interbasin area. Okay. And then we also have stream area ratio, which is defined as the ratio of the area of streams of one order to that of the next lower order. Okay, remember where we are using the next lower order in the denominator and where we are using the next higher order in the denominator. Okay, so that students typically do mistakes here. Then we have watershed shape, right? Then we can have, so this watershed shape again. So frequently occurring shape is how? So mostly that watershed you will see something like this. So it is kind of pear kind, right? Kind of the fruit pear. That's why it can have in the plan view. If you see, it is mostly the pear kind of, but it's not like that. It is the most frequent one which we see, but in the forested catchment, in the glaciated catchment, mountainous one, and all, it can be different based on what is the characteristics, right? So several dimensionless parameters have been proposed to quantify, to quantitatively define this watershed shape, and so for to define or to quantify, we have several dimensionless parameters. Okay, some of them are form factor. So this form factor can be defined as RF equals AW by LW square. Okay, so AW is what? AW is the watershed area and LW is the watershed length. So like that we have shape factor. Shape factor is just the inverse of this form factor. We write that as LW square by AW. Okay. Okay. Then we have elongation ratio. Okay, first we'll see some questions and then again we'll come back. Okay. Because we have a lot of concepts now. Yeah, so we ended with here. Next question we have is basin length is defined as. So just now I have explained this. Can anyone tell me what could be the correct answer? So you see, first option is the greatest straight line distance between any two points on the perimeter. So any 2 points of the perimeter if you consider, and it is the greatest straight line, then we consider that as basin length. This is one of the definition. Next, let's say between the outlet and any point on the perimeter, if it is the greatest distance again, we call that a basin length. The length of the main stream from its source to outlet, which is most commonly used, we call this also as the basin length. So correct answer will be all of the above. Okay, so correct answer is D. Okay, so the next question is the common concept for stream order and Horton-Strahler stream order is. Okay, I'll give 1 minute for this. Let me know if you have any guesses. First you guess and then I answer. Okay, so the first question is, first option is, so we need to find what is the common concept we should know. So the first is, if a third order and a fourth order stream joins, the obtained stream order is common. So let's say a third order stream is joining and fourth order stream is joining. I mentioned that in Horton-Strahler, if third order and the fourth order stream is joining, then the stream that we'll have will be the maximum for both of these. That will be 4, right? So as per Horton-Strahler, it will be 4. And for stream order, will it be 4 again? So let's say if this is the stream with 3 and 4, then the next stream that you will get will be the summation, that is 7, right? So no, this is not correct. So this is not common because we have 7 here and 4 here. Next is, if two third order stream joins, the obtained stream order is common. So let's say if I'll write this as HS and this as S. Okay. So for S, let's say if 2/3 order is joining, then what will happen? And if for HS, so let's say if 2/3 orders are joining, what will happen? So if 2/3 orders are joining in case of hotter standard, we know that the stream that will be forming with these two stream order will again be 3. So we know that when two same order streams joins in case of hot and shallow order, if we consider based on that concept, the streams that will be forming to the next will be the same order that we have, right? But in case of stream, it will be the summation, that is 6, right? So this is also not common. Okay. Next we have both are different methods, so nothing is common. Oh no, yeah, correct. So both are different methods, nothing is common. Whether that is the case, or let's say both are stream order methods, everything is common. Oh, sorry. Yeah. Okay. So I just mentioned that in stream order also, I corrected there first. Yeah, here little correction is there. Yeah. So when two orders with one with order 2 and one with order 3 is joining, then the maximum it will be, right? So it will be 5, 2 to 5, 1, 5, 2 to 5, and 5 plus 1, 2 to 6. Yeah, this is correct only, sorry. Yeah, correct only. Right. It's right only. Okay. Yeah, so is that? Oh, correct. So when in stream order we have seen that when we have, see here, let's see. So when two ones are joining, then it becomes 2. So there is no common thing in that. So the correct answer would be not B. Correct it here. Okay. So the correct answer would be C. Okay. Yeah. And which one? This one was a mistake. Sorry. So when two, three orders of the same are joining, then it will create the order just higher than that. It will not be like 3 plus 3 is 6, but it will become 3 plus 3 and 3 are joining. It will be the next higher order, that is 4. Correct? Okay. 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 So the next question is, if the mean length of first and second order streams are 0.331 kilometer and 0.448 kilometer, then the stream length ratio will be. So how do we define? So how do we define stream length ratio? I just now mentioned, right? What is stream length ratio? Anyone? So I have mentioned right here that what is stream length. First of all, the stream length is the length of the stream or channel of each order, right? So here in the question we have only mentioned first and second order, let's say. So now the stream, that is that to the mean length. So if total length is there, we have to divide it by the total number of the streams, and then we'll get the mean length. So now we have the mean length, and how do we calculate the stream length ratio? That is RL. We calculate it as LU by LU minus 1. That is stream length of the first order or the second order, let's say for here, divided by the previous order, right? So then stream length ratio RL is what? Is the ratio of the mean stream length of a particular watershed, a particular stream order, let's say particular stream order, divided by again the mean stream length only, but for which stream order? Mean stream length of the next lower order. Okay, as I mentioned, just keep in mind that in which, because there are some ratio in which we take the next higher order, and there are some ratios in which we take the next lower order in the denominator. So here second order is how much? Second order is 0.448, and the first order is mean length is 0.331. Just divide, tell me how much you are getting. I will just check how much we are getting. 0.448 divided by 0.331. I'm getting something like 1.353. So the correct answer will be A. That is 1.35. I hope you got the answer. Anyone? Any confusion or any question till here? Okay. If not, we'll move to the next question. Question is, if a second order stream joins a third order stream, the resulting stream order as per the shallow order scheme will be shallow order scheme. We know that, let's say if two streams are joining, one with second order, one with third order, then what will be the resulting stream? It would be 3, right? So the correct answer will be D, that is third. Okay, so the next question is, if A is the area and L is the axial length of the basin and P is the perimeter, then the form factor to define the basin shape. We have just discussed what is form factor. Form factor is the, anyone? Just now we have defined, right? The form factor is defined as RF equals to AW by LW square, correct? Where AW is the area of the watershed and LW is the watershed length or basin length, okay, or the axial length here, axial length of the basin here, and P is the perimeter. The form factor will be simply A by L square. So the correct answer will be A. Perimeter anyway is not detailed in the form factor. Okay. Okay, so the next question is, the area of a watershed is 60 kilometers square. If the length of the drainage basin is 7 kilometers, so we have area of watershed as 60 kilometers square, say W, and drainage basin length LW as 7 kilometer, what will be the shape factor? We have also discussed what is shape factor. Shape factor is the inverse of the form factor. That is, what was the form factor? That was AW square by LW square, right? So the inverse will be LW square by AW. Just put these area of watershed and drainage basin length and tell me how much you are getting shape factor. I'll wait for a minute. Okay, how much we got then? We have 7 square by 60, that is 49 by 60. We have 0.8167, something like that. So the correct answer will be B. Right? I hope you guys also got the same answer. Any question here? Okay, if not, we'll move to the next question. Yeah, so we'll first mention what is the elongation ratio, then we'll come back here. Okay, so I was mentioning what is elongation ratio, right? So elongation ratio can be written as, so elongation ratio is typically the ratio of diameter of a circle, let's say, which is having the same area as the watershed to the maximum watershed length. So it is, again you see, we have, let's say, diameter unit, that is, let's say, meter, let's say, or kilometer, and the maximum watershed length again, so that is also um, in meters or kilometers, the units. So the, again, the ratio is the that is ratio, so it will be a dimensionless quantity. So we write this as elongation ratio as 2 by LW, just A by pi. Okay, so A is the watershed area, which is having the same area as that of, or the same area of the circle that is having the same diameter. Okay, I mean, let's say a circle, if you consider, and one watershed is you consider. So one watershed area, let's say 100 kilometers square. Same watershed area, that is 100 kilometer square, is the area of a circle. So the diameter of that divided by the maximum watershed length. Okay. So what do you think? Let's say if watershed ratio or elongation ratio is less than 0.7, we classify that as elongated one. Now, if it varies from 0.7 to, let's say, zero point 0.8, we call this a less elongated. So now if it increases again, it becomes zero point 0.8 to zero point 0.9. In that case, it will become oval. And if it is 1, then this means what? It is a circle, because the diameter will match, right, to the maximum water length. So as you move more, then what will be, it will be become less elongated and less elongated, and at the end, as per the definition, it will become a circle. Correct? Other than that, we have several other areal aspects like circularity ratio. So let's say if circularity ratio is high, high value, then that becomes, this means it is a having a old stage. So this defines the storage or the stage of the drainage basin, whether the drainage basin is a old stage or if it is having young stage, and if it is less value, it is young stage. Okay, if it is a medium value, then it will be mature stage. Okay, and then then we have compactness coefficient. Compactness coefficient is the inverse of that of the circularity ratio. Correct? Then we have drainage density. So from the definition or from the word only, you can tell what is drainage density. This means that how dense the network is in the drainage basin. Correct? So drainage density is defined as the length of the drainage. So this is the length of the drainage per area or per unit area, let's say. Correct? So this TD is defined as L by A. Okay. Okay. So now, if let's say if some basin or some watershed has high drainage density, this means what? High drainage density means what? High drainage density means a large proportion of input let's say precipitation becomes the runoff. Okay, and less drainage density value means that most of the rainfall will infiltrate. So less drainage density means most precipitation will infiltrate. Okay. Then we have several other areal aspects like constant of channel maintenance, then stream frequency, and so on. Okay, and then we also have in the third dimension, as I mentioned, right? See, in the third dimension we have relief aspects, right? Relief aspects deals with the elevation difference. So in relief aspects also we have several other several dimensionless quantities or several dimensionless numbers like watershed slope, then watershed relief, then relief ratio, dissection index, ruggedness index, and so on. Index and so on. Okay. Okay. So this will do some questions first. We're done till here, right? So the next question is if the elongation ratio is less than 0.7. So it is less than 0.7. This means the shape of the watershed will be elongated one. So the correct answer will be A. It is elongated. Next question is if the form factor is less than 0.76, then the shape of the watershed will be. So form factor was what? Form factor was. Can you tell me the definition or how we mathematically how we write? See, we have just now seen, right? It is the area divided by L square. Correct. So form factor is less than 0.76. This means what? The area is less compared to the square of that of the length. So in that case, the shape of the watershed will be like elongated one or a fern kind of. Okay, so the correct answer will be fern. Next is the ruggedness number is a dimensionless term. We know that, and it is a product of the maximum basin relief. So how do we write ruggedness index or ruggedness number? So ruggedness index Ri equals to the maximum drainage density into the maximum drainage relief. So this is the watershed relief, and this we have seen in the areal aspect, it is the drainage density, right? So the ruggedness number is the product of maximum basin relief to the maximum drainage density. The correct answer will be drainage density A. Okay. Yeah. Next question is for the given study area, what will be the value of relative relief? Remember, this is the relative relief. Okay, so we have two terms. One is absolute relief, which is defined as the maximum altitude of the basin, and then we have relative relief. How do we define relative relief? Or let's say this is defined as denoted as h. This is denoted as h. Okay, so this is the elevation difference between the highest and the lowest point in the basin. Okay, so the question is for the given study area, this is the given study area, what will be the value of relative relief in meters? Given the longest dimension of the watershed parallel to the main flow path is this much meter. So we don't need this because relative relief, what we know as per definition, it is simply the elevation difference between the highest and the lowest point in the watershed. So this is what? This is a DEM map, the digital elevation model map, right? So here from the value you can say, so this is what? This is the DEM values, or the you can write maybe elevation values. Okay, so the maximum is how much? 381 and minimum is 338. So the relative relief H will be equals to 381 minus 38. That is how much we are getting? H 243. So the correct answer will be 243 meters. Here this is in meters. So the correct answer will be C. Any questions here? Okay, if not, we'll move to the next question then. So the next question is high value of the compactness coefficient indicates dash stage of the watershed. So we know what is compactness coefficient. How do we mathematically define compactness coefficient? Compactness coefficient equals inverse of the circularity ratio. And how do we define the circularity ratio? Circularity ratio is the ratio of the basin area to the area of the circle having the same circumference equal to the perimeter of the basin. Okay, and generally this circularity ratio. So let's say if you write circularity ratio, and if you see the stage of the basin, then if the circularity ratio is or value is high, then what I explained that it will be a old stage of the watershed. Correct? If it is medium, then it is in mature stage, and if it is low, this means it is having the young stage. Now the compactness coefficient is what? The inverse of the circularity ratio. This means if circularity ratio is high, this means the compactness coefficient will be what? Compactness coefficient will be low. It is medium, so let's say it will again be medium, and then if it is low, it will be high. So what is the question? That high value of compactness coefficient will indicate young stage of the watershed. So the correct answer will be C. Okay, any question here? Right, we'll move to the next question then. So the next question is the index indicating the vertical erosion of a catchment is what? So while explaining, we have seen that what is which index among these, that is ruggedness index, consistency index was not in this, right? So dissection index. So among dissection index and ruggedness index, which one indicates what? You know what is ruggedness index, right? Just now we mentioned. What was ruggedness index? Ruggedness index was the product of the drainage density to the relief, right? The relative relief. So the ruggedness index, it indicates the stage of geomorphic development of the basin, whereas the dissection index, which is defined as, so let's say dissection index, mathematically if you see dissection index GI is the ratio of H to R. We have mentioned what is H and what is R, right? What was H? H was the relative relief, and what was R? R was the absolute relief. So if you just see the ratio of that, what it will indicate? It will indicate the vertical erosion and the dissected character of basin. Okay, so the correct answer would be C, that is dissection index. Any question here? Okay, if not, we'll move to the next question. So the next question is the process of defining the boundary of our watershed is known as. So we have seen that how we can do the watershed delineation and all. Okay, what is the watershed delineation? Watershed delineation is defined as find the word delineation. If you see, what is the meaning of the term delineation? The term delineation means like if you identify the boundary of a catchment or any boundary of any region, we call that as delineation. So identifying the boundary or the watershed divide or watershed boundary, whatever you call, if we find out the boundary of one watershed, we call that process as watershed delineation, right? So the process of defining the boundary of a watershed is known as watershed delineation. Okay. Okay. Next question is, what is the purpose of filling sinks in a dam before performing watershed delineation? So when we have seen the QGIS part, right? So in that, we do one fill sinks. We select one fill sinks option, right? So fill sinks option again, it is given by several other researchers. So you'll see different fill sinks by different researcher methods. Okay. So what is the purpose of the filling sinks in a dam before performing the watershed delineation? Anyone? Why do we fill sinks? So in a dam is the primary input that we need for watershed delineation. If we don't have dam, we can't do. So like, if one more question is, let's say if this digital elevation models and all given by the satellites and all is a very not very old phenomenon, right? So it is maybe if you consider 1980 something like that, so nearby that we have started getting these data. Before that, how people used to do the delineation? Before that, people used to use the topographic sheets or topo sheets we call, and based on that, based on the elevations that we have in the topo sheets, we used to delineate one watershed. Okay, now coming to these questions. This question is, what is the purpose of filling sinks? So why do we fill sinks in this dam? So the answer will be, so let's say the dem whatever we have downloaded from somewhere or whichever satellites product is giving us the dem data, in that it might be possible that there are some errors in the elevation, right? So to correct that errors in the elevation, we we do the fill sinks. So why we are correcting these errors in the elevation? We are correcting these errors in the elevation to ensure proper flow direction. Otherwise, what will happen? So let's say if some water is flowing, right, and there is some depressions in it, what will happen? The water will will get stuck in the depression. But in the ground truth, if you see, there will be no depressions there, and hence the flow direction will change, right? So to ensure the proper flow direction and to correct these errors in the elevation, we do this we use this fill sinks option while delineating the watershed. Okay, so the correct answers are B and C. Okay, any questions here? Okay, if not, we'll move to the next question. Next question is, what does the flow accumulation tool in QGIS? Okay, sorry, I don't know. What does the flow accumulation tool in QGIS compute? So there is a tool called having flow accumulation. Can you tell me what does that tool used for? So we use a flow accumulation tool to identify or to determine the number of upstream cells that are contributing to each cell. So let's say if you are in a cell, so let's say if this is the watershed and this is the stream, let's say, and you are here in this cell, let's say. Okay, now in this cell, you are using, let's say, flow accumulation. So what happens? Whatever upstream cells are there. So before that, there are several these resolution cells are there, right? So all the flow will accumulate to here if you consider this outlet point or this cell. So the number of upstream cells which are contributing to this cell, we can use the flow accumulation tool. So the correct answer would be B. That is the number of upstream cells contributing to each cell. Okay. Next question is the resolution of the DEM. So we have seen that DEM data can have different resolution based on what satellite you are using. In the current resolution, if you have seen, it has improved a lot if you consider maybe 20 years or 30 years back, isn't it? So this why we are behind this resolution? Why we want to improve this resolution of the DEM data? Can you tell what is the resolution of the DEM used in watershed delineation? Why? So if we change the resolution, so let's say if you are taking one DEM data which is having a 30-meter resolution, and one depth data which is having 90-meter resolution. In that case, what will happen if there is a high resolution depth data? In that case, what will happen? The flow direction will be much more clearer. Okay, the number of streams that will extract will be more. The size of the watershed boundary will be much clearly we can delineate. So the correct answer will be all of the above. Okay. Okay. Next question is, yeah. So the letter E in the acronym POWER, explaining the concept of watershed management. So while studying the watershed management, we have seen that we consider one acronym called POWER. In that, each of this letter denotes something, right? In the watershed management. Can you tell me what does the letter E denotes? Mhm. And we know why we do watershed management and all that we have seen in the lecture. I'm not going into that. So this letter, that is P. What does P denote? P denote the production of all this, let's say food, fruit, fiber, anything like that. Okay, so that uh, how we can produce this on a sustainable basis. What is sustainability? Sustainability is like whatever resources we have right now, how we can use that so that it is also available for the next generation. So it's not like what thing we should have. It should not be like, okay, these resources are there, we can just use that because we have this. It should not be like that. We should have sustainability in our mind, because whatever generations are going to come, we should think for them also. So the resources that we have, we should use in we should use those resources optimally so that our needs are fulfilled, as well as the resources can be left or can be used for the coming generations also, right? Okay, so production of food, fodders and all, then pollution control, prevention of floods, so all this comes under P. Then O means over exploitation of these resources to be minimized or to be optimized by controlling the excessive biotic interference, like overgrazing or something like that. Then with O we also have operation practicability of all on-farm operations, something like that, right? Then we have W. What is W? W is like water storage at convenient locations for different purposes. So let's say if we have dam, how how much we should release water from that dam so that we can fulfill the needs of the downstream people. The agriculture that we have can be properly irrigated, and let's say some urban area is there, how the water should be allocated to each of the households and so on. So this should be done optimally, right? If we, let's say if we release a lot amount of water, it might be possible that the agriculture can get affected. Or let's say if we have given high number of a large amount of water is released, the downstream area can get affected, the downstream area can get flooded and so on, so many things. Or maybe now we have released so much of water people have used, but after some months it can be possible that in that area a drought like situation is there, but we don't have water. So the water that should not be released at that time can be used, we would have used at this time. So like that, we have to think for the water storage at convenient location. Then for W, we can also have wild animals and indigenous plant life conservation at selected place. Then we also have E, which is the question here. So E can be have erosion control, then employment generation, economic stability, ecosystem safety. So for now, we have all these options correct. Then we have R also. What is R? R is like rainwater harvesting, groundwater recharge of groundwater, then recreational some methods, then reduction of siltation, reduction of drought hazard, and so on. Okay, so for this, correct answer will be all of this. So symbolically we used power, but when they made it, it is also based on power transfer. That is that real power to the beneficiaries by improving the socio-economic plot. So there have been several watershed management that we have seen in India before independence, after independence, in the rural areas, and so on. Okay. So whatever development projects are there, I'm not going very deep into that. You can just go through the lectures and all. Okay. So next question is DPAP. So this is one of the watershed management policy given by the Ministry of Rural Development. You have seen Department of the Land Resources. So this DPAP stands for. Can you just guess and tell me how what will be the answer? The correct answer will be drought prone areas program. Okay. Okay. Next question is the first letter of a watershed coding for a particular watershed refers to. So when we do this watershed management planning and which watershed to be prioritized and so on, what we do, one of the steps is to code that watershed. Okay, because let's say if a very big name is there and it can have several properties, it's very tedious to write all the things at one place and so on. And that's why what we do a watershed coding. Okay, so the first letter in that code, what we do, the main river or let's say the mainstream whatever is draining the watershed is identified, and the first letter of that name we consider that as the first. So let's say one code is like maybe RN to R, something like that. So this R will represents the name of the mainstream. Okay, this N means natural. Okay, so the second will be the name or type of the watershed is identified. So it's if it is a natural subcatchment, then it will be N. Okay, something like that. Now, if third, you will see third there is a digit. Now, the digits of the watershed delineated within the watershed are used. So, the digits for the watersheds delineated within the sub watershed that are there are used. So, here we have two sub watersheds, let's say. And the last is R. The coding typically starts from the downstream end and proceeds to the upstream end. And the tributaries are, so we do this coding for all the sub watersheds also, small watersheds. So it basically starts from the downstream and then we proceed to the upstream end. And the tributaries are considered with respect to their joining side. So let's say if it is for the mainstream, it is joining from the left side, then we write L, or if it is joining from the right side. So this means what? This is right tributary. Okay, if it is joining from the right side, then we write R. Okay, so the question was the first letter of a watershed coding for a particular watershed refers to identify the main river of or stream draining the watershed. The correct answer will be A. Okay. Okay. So the next question is sediment yield can be obtained. So while doing the watershed prioritization, what we do, we use several indices such as sediment yield index. Sorry. Sediment yield index or runoff potential index, something like that. So these are some of the indices which we used to prioritize the watershed, like which watershed to be prioritized, which is having high priority, which is having low priority, so that we can plan the management of that watershed. Okay, so to know this sediment yield index, firstly we need to know the sediment yield, right? Because sediment yield index, what is the definition for sediment yield index? Sediment yield index is like defined as the sediment yield per unit area. Okay, so SYI is the sediment yield divided by the area. Okay, so it is obtained by taking the weighted arithmetic mean of the products of erosion intensity weightage value and delivery ratio over the entire area of the hydrologic unit. Okay, so the main concept that is behind this sediment yield is in the option you can see two concepts are there, that is erosion and erodibility, or erodibility, right? So what is erosivity or erosion? Erosivity is the rainfall characteristic considering what is the intensity of the rainfall, at what angle the rainfall is coming, at what frequency the rainfall is coming, what is the duration of the rainfall, and so on. Based on that, erosion will vary. Whereas what is erodibility? Erodibility is the soil characteristic. So those this is the rainfall characteristics, and the erodibility is the soil characteristics. So these are the two things characteristics that affects the sediment yield, right? And how will we get the sediment yield? Then sediment yield will be equals to erosivity into erodibility. So the correct answer will be B, right? Okay. We'll move to the next question. Sediment yield from a catchment is a function of, just now I mentioned that it will be both erosivity and erodibility. Okay. Okay. So the next question again is, the erosion intensity or runoff potential weightage values are assessed based on which of the following factors? Yeah, I know tell. So let's say if land use land cover changes, then the erosion intensity will change because the soil is changing. Not only that, but the runoff potential will also be changing because let's say if one land use is uh, bare land, barren land, and then it is covered with, let's say, roads or something like that, so it becomes impervious. In that case, the runoff will change. So because of that, the runoff potential weightage values will change. Like that, if slope is changing, so slope is again the soil characteristics, the erosion will change, and not only that, but runoff will also change. So climate also. So correct answer will be all of them. So the correct answer will be D. That is all of them. Okay. Next question is, the below figure shows the contour bunding. Okay, this comes under which of the following component of watershed management? So while this watershed management and all, we can have several components of this watershed management like land management, then water management, biomass management, and so on. So we can manage this watershed into these three components of the watershed. Okay, so this is one of the method that we can use to optimize or to control the several factors like erosions, water retention capacity of the soil, and so on. Okay, so this, okay, let's come to the contour bunding then. This contour bunding is one of the measure which we do. Can you tell me which are one of the following component of watershed management it will come under? So it will come under the structural measures of the land management because we are working on the land, right? So what will be the water manage or let's say water management? Any example for water management? Any example for water management? We can do rainwater harvesting, isn't it? Then groundwater recharge and so on. Okay. So for this, correct answer will be structural measures of land management. Option A. Okay. With this, we end today's tutorial. Any question till now? We also talked about. So we have also seen the planning, integrated watershed management. Any question till now? If not, we'll stop it here. Integrated watershed management. That is IWM, right? So I'll not go detail. We have studied this in lectures. Any questions in this, or any doubt? Anything in the questions today? Okay. If not, we'll stop the session here. Thank you. So we'll be again, you can join next Monday for the next lectures. Thank you.